Okay. Alrighty. 1 second. There we go. The camera's looking down quite a bit today. There we go. Hello, hello, hello. How are we all? Hello, everyone. So, welcome to week 10. We've made it. The very last week. That's exciting. I am great, thank you, Mitchell. And I'm glad you are great too. And hello everyone else who have been having fun putting your crab emojis in the chat. All right. So, welcome to week 10. What have I got to get out of the way before we get started? Well, your assignment 1 marking should now mostly be released. There was some, like, when we were actually releasing the marking, rather than, I say we, when Tom was, who has been putting in a lot of really hard work, was doing the work to release the marking, it turned out there was some internal issues on our end with some of the marking. And so a few students may not get marks, or we may have had to send an email saying, hey, we need, this from you or that from you or that kind of thing. If you happen to not see marks for it, like, don't freak out. It's almost certainly not even your fault at all. But you should be able to collect your marks here, or using a command on a CSE machine. And overall, everyone, like the vast majority of students, did really well in assignment 1. So congrats to everyone. It was really sort of fun seeing, especially like when I was, marking my portion, reading through like mark requests and seeing you all sort of like talk about your designs. It might just be me sort of reading into it too much, but I sort of got the impression that for a lot of students, they were like, sort of somewhat passionate talking about their design, going, oh, I did this for my quest system, and I think it really made like a nice design. And I made it really generic and flexible, and blah blah blah, or like I used this feature over here in my adventurers terminal game, and it just seemed like, when I was reading it, I personally got the impression that a good chunk of students seemed to be having a fun time with it, and were genuinely happy and proud of the code that they spat out of the that you ended up submitting. And it was great to be able to do, for the vast majority of like the submissions that we got, be able to go, great work, and here's a lot of marks to reward that. So yeah, great work to everyone. Have a look at like what you've got. You might have a small amount of feedback. Some of the so you may find throughout your code there might be some like quad / comments, where when we're marking, if we feel it's necessary to add some sort of like inline feedback, we've thrown in like a quad / to sort of distinguish your own comments in your own Rust doc from things that we may have added. So if you're looking for, there may be some inline feedback. Particularly students who did particularly well might have like quite little inline feedback and just the overall sort of marking. And there might be some high level ideas briefly talked about in the marking, like the marking file, finalmarks.txt or something like that. But yeah, have a look at that. Take on, if you think it's reasonable, take on the feedback any feedback you've been given for your assignment 2. Continue working hard on that. Ask any questions, clarifications, that kind of stuff on the course forum. But yeah, just once again, congrats everyone, and good luck finishing out your assignment 2s, which are due I want to say Friday, but I'm going to double check. And the course website is slow. Yeah, week 10 Friday. So this week Friday at 5 p.m. So don't miss that one. Remember 5 p.m. Some people got this a little confused. I think next session we might make sure our weekly exercises and assignments are due on the same hour mark. But just be very clear, it's 5 p.m. Although, you know, even if you end up submitting it at 9 p.m. or 9 p.m. anyway, 4 hours is such a small reduction off your mark. Like 4 hours is 4 out of 24 times like 5% per day. You're looking at like an 80% of like one, like 80% of one mark in this assignment, and this assignment is worth, I want to say 25 marks in total, something like that. Assessment is worth 25 marks in total. So like and you're looking at a quarter of this for a course mark. So you know, you really like take on the maths and you're like, okay, this is such a small portion of anything. But just be aware of all that. Don't forget your week 9 weekly exercises, which are due not the usual Wednesday, they're the Thursday instead, just because we released them a little bit late. But there's 3 exercises, and it's been noted that these exercises don't involve writing a ton of code. Rust to C is probably a couple lines of code at best, like maybe 5 lines of code or so. Unsound Unsafe is literally like maybe 2 lines of code. MyRC is probably like maybe 10 lines of code, something like that. So these exercises, overall, you're probably writing 20 lines of code or so between the whole week, but it's about writing the correct code and trying to make sure that you're that what you've written is correct. So make sure you've had a crack at that. The week 10 exercise, right, week 10 is released. I just need to do a hard refresh. If you don't see week 10, you might also need to do a hard refresh. I did Control-Shift-R. And it is it says live exercises. It's a prac exam that we've given you. So this here is is like a mock, exam based on what your final exam will look like. I would suggest trying to take this yourself under exam conditions. Given we've already finished the content of the course, like the official accessible content of the course, I would suggest everyone to take this like as soon as you are reasonably able to, because the sooner you take it, the sooner you'll be able to start working on the bits that you might have had more trouble with, or to ask questions about it, or bring questions and stuff into the workshop. So I would suggest giving this a crack whenever you have the time to do it. Notable points are that the exam is open book. It's standard, otherwise pretty standard exam conditions. You're not allowed to communicate with other people. You're not allowed to work in pairs or groups or anything like that. You're not allowed to write to the internet. So you're allowed to access the internet. Open book meaning, I guess there is a distinction between open book of like just your own notes, or open book you're allowed to access the internet. We are saying that you are perfectly allowed to access the internet, but only to like read resources, right? So you can Google how to, how to implement trait in Rust, and go to Stack Overflow and see someone else has asked a question and go, okay, I just needed to jog my memory. There it is. But you can't say go on Stack Overflow yourself and ask a question, how do I implement a trait in Rust? So you can't post anything to the internet. You can't essentially write to the internet. You can only read. You have a shared borrow on the internet. That's another way of putting it. You have a shared borrow on the internet, not ownership and not an exclusive borrow. That post would be deleted by Stack Overflow mods. That's true. And so the exam is I think I've mentioned this in a few workshops, is far more heavily theory than you've seen throughout the rest of the course. Theory in quotation marks here. This is because like we were considering, the course not even having a final exam at all when we were, constructing the course originally. But the final exam basically exists to, we're going to get you to do some form of implementation, but a big part of the final exam existing in the first place is so we can ask you written questions and that sort of stuff that sort of draw upon what you've learned throughout the term, and you can sort of answer and freely and that kind of thing. I don't want to spoil the questions themselves, so let me just double check the ratio here of what we've got, the ratio between theory and practical questions. So question 1 has and I'll note that some questions have subparts. So for example, without showing you the question itself, you can see question 1 starts with 1.1, which is worth 2 marks. Question 1 has 4 subparts that are all written, theory. Question 2 is a practical programming question. Question 3 is a practical programming question. Question 4 has 3 subparts that are all written theory. Question 5 has 4 subparts, that's all written theory. Question 6 is practical programming. Question 7 is 2 subparts theory written. And question 8 is no subparts but written. So I think in total I counted 3 practical exercises. Yep, that seems right. And 5 sort of written theory-based questions that are that may include subparts, sub-questions that we're asking. Shared borrow meme, yes. Writing info to Google Analytics, yes. So there is certainly a limitation of reasonability that we ascribe to the idea of writing to the internet here. 5 theory, 3 prac, going to be like old school 152 on exams. Yeah, I guess you could think of it that way. Yeah. Also, we're not guaranteeing the split of subparts will be the same, but the split of prac theory should be. Cool. There you go. So it should be genuinely a pretty good representation of what your final exam will actually look like. So again, the best way to get a gauge for how you're looking for the final exam is to set this practice exam yourself in exam conditions. Cool. It's worth noting. Okay, so earlier I said I put theory in air quotes. The reason I put theory, prac/theory here in air quotes, is because we don't plan. So this may be the case, like some questions this may be the case, but we don't generally plan for all our theory to simply be, tell us like what this thing is in Rust, right? Like a sort of theoretical question that has a pretty well-defined answer. So you can imagine a theory question from like a mathematics course being like, here's some equation, solve for this variable, whatever. In which case you're going to write some, you're going to write some stuff and find a value, and there's generally going to be one correct answer. Whereas we're planning to ask, for the most part with these theory questions, as you'll see when you take the exam, the prac exam yourself, they're far more open-ended. They're more about asking you to sort of share your opinion on a given scenario, and to back that up, like substantiate that with arguments based on what you've learnt throughout the term. So, for example, you might come into the final exam or into the prac exam here going, I really hate Rust. Like this whole term, this has been an absolute nightmare for me, and I think Rust has just gotten everything wrong. And that's okay, as long as you have like good reasoning as to why that's, the way you feel. You might have gotten here going, oh, Rust is the best. I really love Rust and I love the way it does everything. And in sort of the same vein to this, just going through the exam being like Rust is amazing is also not going to get you marks. So you're not going to lose marks by being like, I don't like Rust. You're not going to get free marks just by going, I like Rust. So it's about like hearing a scenario and going, this is what I believe, right? This is the way I sort of feel about this situation, and here's why. And you know, if it's a, you know, if it's a well-supported argument that backs up your position, then, you know, the arguments is where we're sort of giving you the marks in this case. Now, there might be a small amount of questions, like especially just sort of easier questions that we're just trying to give you some sort of more like freebie-ish marks, sort of maybe leaning you into the exam, and you know, just giving out some sort of some easier ones. We might just ask straight up questions where there's expected to be some sort of answer, and like, so you need to be able to expect and deal with things like that, but that's not going to be the dominant theme throughout the exam, is what I would say. Okay, so just realized since this course is new, you guys have to write 2 exams. Yes, we do. And the workshop will have some sample questions, Tom says. Yes, it's been very fun for sure. Honestly, like, yeah, exam stuff has been surprisingly fun, because I think writing questions that actually put you in these hypothetical scenarios and get you to do thinking and reasoning is pretty fun. Cool. Is there anything else that we want to call out about the exam, Tom? Just to be clear, most practical questions you'll get some sort of starter code, and your job will be to like implement something. Most theory questions, you know, I went through and I was reframing them as sort of like fun, you know, changing the questions from like, tell us about this, to like, Steve is trying to write some Rust code to do blah, 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 and does this, you know, here's this. Oh, actually, he realizes that he needs to do this instead. Give an example of blah that Steve might be trying to do, where the first thing is not good enough, but the second one might actually work, and explain us, you know, why that, you know, that it's pretty fun. And if you go through the prac exam and there's things that you find that you really didn't like about it, or things that you found confusing, you can also let us know that, and that could potentially, to a like minor extent, influence the final exam. In that we're not looking for you to go, I really liked the questions that were around like the week 1 and 2 topics, and we'll go, great, we'll make the whole exam on that. But it might be like, I didn't like the wording of this question, and we can try and make sure we, you know, potentially avoid that kind of thing in the final. Mention what Q8 is. All right, why not? If you don't want to know what Q8 is, then you might want to, you know, switch off the lecture for a second. Maybe I won't show you it entirely, but Q8 for the prac exam, and I think I'm fine saying for the final exam, we plan to be relatively open-ended. So we expect that the exam should hopefully be completable by someone who has like put, you know, the work in and the study in and is doing well in the course. The exam should be vaguely, like roughly completable within 2 hours or so. But it's scheduled to be sit over a 3-hour period. But with that in mind, the final question, Q8, is, okay, the idea of Q8 is, here's a larger thing over there that we want you to go have a look at, and then we're going to give you some kind of a prompt, and then you have like as much room as you want, whether you want to, you know, answer it very quickly if you're in a rush in the exam, or if you want to put in a lot of work and write a very big response. You can sort of discuss a certain prompt, and put in a lot of your thoughts, and we're hoping that, you know, whatever we give you, there'll be plenty of meat for you to chew at. Plenty of things for you to go to talk about if you have the time to do it and the willingness to. And so it'll be sort of, yeah, more open-ended final question in the exam, which again you'll get a try of in the prac exam. Cool. Any other things, Tom? Tom has been very much putting in a whole bunch of work for all the exam stuff, the final exam and the prac exam and all that. So a massive big thanks to Tom. I mean, everyone should hopefully already be aware of this, but I'm just going to make it abundantly clear as well. The exam, the final exam itself is all online. You're not coming into CSE or the CSE labs or anything like that. And it's not proctored, meaning we're not looking through your webcam. You don't have to install some dodgy software to take the exam. It's just going to be almost like you're doing weekly exercises, but in exam conditions, at home or yeah. Cool. Yes. All right. So, yeah, make sure you read through all of these as well. These should mostly be the same for the final exam. So, what time is the exam? I know it's on Tuesday 6, but I can't recall the time. So, it is a morning slot. It should be 9 a.m. Yep. So, the final exam is Tuesday, the 6th of December, 9 a.m. to 12 p.m., 3-hour exam. There was someone mentioning, we got some feedback going, this time slot is relatively inconvenient, given a lot of people, need to go to work and that kind of thing from 9 a.m. And sadly, we have no control over this time slot. I believe we asked for an afternoon slot, but you sort of, exams are centrally timetabled at UNSW, and you get what you get. So, our apologies. But that will be the time at the final exam. Of course, the prac exam you can do as you please. Write your own proctoring AI, write your own borrow checker, write your own Rust language offshoot. Yes. Oh, yes. Thank you, Tom. Yes. If you, this time slot, 9 a.m. to 12 p.m., if that is a horrible timing for where you live, if you live, I think within Australia, you probably, I guess in Perth, you'd be 7 a.m. I think that's still within, I think UNSW would consider that to be fine still. But if you are overseas, where this time turns into something ridiculous in your local time zone, say, you're overseas quite a few time zones over, and this turns into 3 a.m. to 6 a.m., you should very much be applying for special considerations, and saying that, hey, this time is ridiculous in my time zone. I'd like to take it at a different time around the same, date or whatever. And they'll be able to hook you up with that. And I think there is documentation. I've seen it before, I believe. There's documentation about how far out of, what hours in your time zone it must fall in for you to be eligible for this, for the special consideration. But yeah, if it's a ridiculous time for you in your local time zone, you should apply for special consideration. Okay, and Tom says 10 p.m. to 7 a.m. He seems to have found. So, double check your own things and make sure you apply. But if it's looking kind of crazy for you, don't worry, you'll be able to get it moved to a more reasonable time. Okay. I guess that's probably it. Tom seems to say that was mostly it. Cool. In that case, we're going to have some fun. So, to be clear, this is a for fun lecture from this point forward. We've talked about the prac exam, and I guess we've mostly talked about the exam as well. These exam details plus what you've seen in the practice exam is basically the information for the final exam. Otherwise, just make sure you don't forget that it's here, and make sure you don't wake up at 10:30 a.m. and go, oh my god, it's halfway through the final exam, because one student always manages to do that. One student always manages to either oversleep or forget that there's an exam every session without fail. So don't let that person be you. So yeah, anyway, I guess if you have further questions about the prac exam or the final exam, direct them to the course forum. Otherwise, I mean, yeah, again, we're then out of things for the lectures again. So everyone go home, switch off the lecture. No, so we do have some fun stuff we can talk about. We are going to try something this lecture. So I'm going to try and talk about Async Rust today, and maybe on Wednesday we'll have to see what there was some other interesting ideas to maybe fill in. Called it, yes. So let me lay some absolute ground rules for what we're talking about here, and expectations. So many people have asked me during the workshops, can we talk about Async Rust? I've seen so much about Async Rust. Can we do Async Rust? Yes, Async Rust is very cool. In the real world, it's very popular. However, there is still work being done in the language for Async Rust. There's sort of bits of the language where Async Rust is particularly tricky, or isn't quite flexible enough to support things that we want just yet. But it is still, for the most part there, it's still very much used, and there's some really cool things that live in Async Rust. For example, the Tokyo executor is is a seriously cool piece of technology, in my opinion. And there's some really awesome projects that leverage lots of different parts of Rust in order to provide really cool interfaces. Rocket is a pretty big favorite of mine. And so there's still just a ton of interesting stuff to play around with. We're going to try and talk a little bit about the weeds today, sort of some of the low level details and how Async Rust is sort of formed, and maybe contrast some approaches in different kinds of languages. But let me make a couple things absolutely clear. This is kind of difficult content. This is not accessible content. This is not going to be stuff that appears in the exam. It's not going to be stuff that we're marking you on. It's just for fun and for interest. You are still allowed to ask as many questions as you want. You can still ask things on the course forum about this stuff. But it's our own sort of for interest topic, and it's not going to be, and it's not something that you should be stressing out about or digging your head into the books to study for if you're worried about the rest of the content for things like the final exam. So with that in mind, who is ready to talk about Async Rust? Wow, Async Rust. What lec is this? Lec 17. Wow, we've come so far. Look how many lec folders there are. Wow. Okay. So let us start by talking a little bit about what Async Rust means. Because you might just hear the word, async, and, insert language here, Async Rust, and mean, well, async here is short for asynchronous, which, I mean, technically async is short for asynchronous, and Rust here is a programming language. So when people talk about Async Rust, they must be talking about doing, asynchronous programming within Rust. And that's not usually true, sadly. So asynchronous, to be clear here, the terminology asynchronous here literally just means like A being the someone who knows about English syntax and stuff can remind me what like this prefix here is called. But it just essentially is a word meaning not synchronous, and not synchronous meaning like we tend to think of our code as being sequential by default. It does this line, then this line, then this line, then this line, and sort of flows in one direction, and is very much sequential. That's our sort of typical model of synchronous programming. You go asynchronous when you start thinking about code as not simply just being synchronous, but perhaps say executing in multiple locations at once, or executing one thing and then going and executing some other thing and then coming back and executing this. And so that's where this sort of idea of being like, well, okay, I must already know Async Rust, because in the course we've done things like stood thread spawn, and that lets us start being asynchronous. Right now we now have like our code is continuing over here, and it's now also continuing in a separate thread over here. And so we are writing asynchronous code, but it is not generally what people talk about when they talk about Async Rust. So Async Rust is not really just a sum of async and the language being Rust. It's a specifically different idea that just falls under the name of Async Rust. And this is what we will discuss now. So, what is Async Rust all about? Async Rust is all about, to me, I believe Async Rust is all about something called stackless coroutines. It's all about stackless coroutines and how they sort of work with Rust's future trait, the future trait. So, all right, stackless coroutines and the future trait. So what are we even trying to do in the first place here? Like, what is the problem that Async Rust is trying to solve? So I mentioned before that you might think about, someone might mention, asynchronous Rust to you, and you go, I already know how to do asynchronous Rust. I know how to use threads. Since I know how to use threads, I know how to write asynchronous Rust. Like, therefore, I've got it. I've got it figured out. And like, that's true, but it's not really the whole story. So what do I mean by this? It's kind of like what we've done. So imagine someone was talking about the idea of generic programming. Programming is apparently what I've written. Generic programming, right? Where let's say like the idea of generic programming being I can write one piece of code that works generically over many different, types. Say this might work for a string or an int or a whatever. And imagine that someone was like, hey, I want to talk to you about generic programming. And you go, oh yeah, I know generic programming. I use vec all the time. Right? Or vec of t, I suppose. I know generic programming. I use vec. And it's like, yeah, okay. Like, you probably have an understanding of generic programming then, if you know how to use vec, vec of some generic type parameter t. But would you really say like you understand generic programming sort of as a general concept if you've just used vec? Like maybe you've really figured it all out from there, but most likely you've sort of figured out a way to use generic code and roughly how generic code can work, but you might not understand the principle, like the sort of abstract idea of generic programming. And this is maybe gonna hurt a little bit. It might hurt to hear this, so brace yourself a little bit. But this idea of async programming is kind of, to a certain extent corresponds with this example over here, where I know async programming because I know how to use threads. And it's like, yeah, threads are certainly a tool for async programming, but they're not necessarily like the absolute primitive, and threads don't represent, async programming as a whole. there's actually a lot more ideas that can come into it. And so what we're going to start off with is trying to understand, we talked about like principles of async programming a bit when we were first getting started in week 8. Yeah, week 8. But we're going to recap on that and then see how Rust tries to represent that generic idea in a generic manner with essentially what we have up here. Okay, so simplify the process of doing multiple things at once, but without the complexity of threads. Yes, that's certainly what they're trying to do here, and so yeah, we'll certainly be talking about that. Right, just to recap. Actually, does anyone want to recall in the chat? There was something that I mentioned at the beginning of week 8 when we were just first introducing the idea of concurrency again. There was this nice quote from Rob Pike, which talked about one of like the premises of concurrency, why we care about concurrency in the first place and what concurrency really means. Does anyone want to offer in the chat either if you remember roughly what that quote was or what you think concurrency generally means? Right, yeah, awesome. So concurrency is the idea to handle many things at once. So there was also that idea of parallelism. Parallelism meaning like being able to literally do many things at once, but concurrency is more about the idea of handling many things at once. So async programming, one of the fundamental ideas is being able to handle doing many things at once. So when we think of Async Rust, we usually think of these many things at once, right? Like, what are the many things that you're trying to many at once? What are those things? Generally, these are some kind of like, I'm gonna call it like an IO bound task. So this is maybe not generic enough to mean what I want it to mean, but like what I'm more like sort of specifically looking for is like not CPU bound, right? So tasks that are not CPU bound, meaning they're going to take a certain amount of time and it's just the time that the CPU, like the CPU in this computer, needs to put into it. But instead tasks that might take a while because we're waiting for something else. We're blocking on something else. And yeah, a blocking task, you could also call this, but even CPU bound tasks, you could argue are occasionally blocking. Like this might block for a few seconds until the computation concludes. So what we're specifically interested in are tasks where we need to do something, but we're probably going to be waiting for someone else. So a example of this is something like a web request, and we've talked about this all before, but let's go a little further than last time. So there's a crate called request. Gosh, I hope I don't run out of disk space during the lecture. So there's a crate called request, which is fun, that lets us basically quite easily make HTTP requests. Cool, and it has about 100,000 features that you can switch on and off, which is great. Do I need, and I want this feature, I think it's -A, or is it, no, feature blocking, features blocking. There we go, cool. So if I want to say get the Rust website, I'll let Rust Analyzer do its thing in the corner. If I want to make a web request to get the Rust website, get, then I might do something like this. I might say unwrap it, and we'll get it as text. That seems like a good idea. Unwrap that, and this, I believe, should be let response is this, and this is a string. Yes, string. We can see that here. Cool. So I might say something like println sending request to rustlang.org. Then we'll say received response from rustlang.org, and then maybe print out the response itself. Response. Like that. Okay. So if we run this program, we're going to see something like this. Oh gosh, we're going to see a huge compilation. Let's build it first so we can actually see it running sort of separately. All right. So if I say run the program, we see sending request to, man, I should, let's throw this in something like Vim. Okay. Damn it, it buffered it too much. Okay, here's what we'll do. Run pipe head -n30. So we see sending the request, receive the response, and then it spits out the page itself. And this here, like to go from sending this line, this print, and actually receiving the response takes a bit of time. Maybe 1.5 seconds or so. In fact, I guess we can actually time it ourselves. It took 1.135 seconds or so, right? That is not time where if I had a billion CPU cores, if I was running this program on an absolute supercomputer, it would run, you know, a computer 1,000 times faster than mine, it would run 1,000 times faster. If I run it on a supercomputer, right, in my house, if I manage to fit a supercomputer in here, it's probably still going to take about 1.1 seconds or so. Is just sort of like the fact of the matter. Because the thing we're waiting on is not my computer being slow, it's waiting on rustlang.org to give me back this information. So as our program exists right now, there's really no reason for there's really no reason to even worry about asynchronous programming, because all our program wants to do is get a request to a website and then spit it back out. But as I mentioned, you know, in week 8, what if we want to do something like this? So what if we wanted to say, you know, do this process, but also, what's another website that's probably going to be slightly slow that people are interested in? Maybe like the C++ reference site. How about that? That's a good one. That'll probably be sort of slow. Sure, that seems great. So we go send request to, well, let me put this here. Sending a request to c++reference.com. Oops, that's not what I want to do. Also not what I wanted to do. Here. To C++ reference. There. And receive response from C++ reference. Cool. And here's that response. Right, let's see how this program works. Also, this response is going to be really long. Let's just change this to be response.lines.next.unwrap. Just grab the first line. Same with you. Response.lines.first. No, sorry, not first. Next, sorry. Next.unwrap. Like that. All right, let's build it and let's run it. Yep. Sending request to rustlang.org, sending a request to C++ reference. Wow, look at them. They can't agree. Now, this program takes about 2 seconds, right? Because it's waiting about a second for rustlang.org and it's waiting about a second for C++ reference, right? But like, it didn't have to be that way necessarily. It didn't have to be that way. And we know with threads, like now that we've learned this in the course, we could rewrite our program to do this first one here on a thread, say. So we could say something like, or even I guess we could do them both on their own threads. In fact, that'll maybe be slightly easier for us. Let's do std thread scope, create a new scope, then grab all this stuff here. This will be scope.spawn until here, like something like that. And then scope.spawn, and we have something like that. All right, how about this? So now we spawn two threads. One thread asks Rustlang, one thread asks C++ reference, and let's see how this program performs now. So it's still, oh, I was reading the wrong time this whole time. What? No, was I? 2 seconds total. Where's the wall clock time? Am I going crazy? Oh, okay. I don't know what happened. I think we just got a weird, some fun weird edge case over here. But this is what I was expecting. Now it takes 1.1 seconds still. I guess one of the websites just took slightly longer that time. There we go. Okay, cool. That was weird. Oh, I counted the rebuild. Oh, you are so right. The rebuild took 1 second. Very good. Awesome. Thank you. So now, even though before we did this, which was up here, we still have the same information and the program took 2 seconds, we managed to basically double the performance of our program by essentially asking, like kicking off the process of telling Rustlang.org to give us its bytes and asking C++ reference to give us its bytes. And we only end up having to wait essentially as long as whoever takes longer. In this case, it looks like C++ reference is slightly faster. I mean, can we even see it? Yeah, you can sort of see like dirt from C++ reference and then dirt from Rustlang.org. And so we've, it's like we've effectively made our program twice as fast by using threads, by leveraging concurrency. So let me just catch up. Python website would surely be slow. Python.org. That seems pretty quick. Let's throw it in quickly just for fun. So, and this is a relatively scalable method. In fact, this ties in nicely to what I'd like to talk about anyway. This is a relatively nicely scalable method in that if I want to add another website, I can just sort of like, you know, I can just go in and add another thread that does this. And we're going to say python.org, Pythonorg, okay, like this. And I can run the program again. I can build the program again and then run the program again. Yeah, look at Pythonorg. Lightning fast. And the program again is still taking just 1.1 seconds. Like it's taking the exact same amount of time as it was before, because we're not waiting for the computer to catch up, we're waiting for everyone else to send us the information. No realistic C++ thread didn't segfault. Okay, so this is really interesting. And threads, we've learnt, let us leverage concurrency in order to let us think about many things at once without necessarily doing any two things at the exact same time, truly in parallel. Website speed inversely proportional. Okay, so then what have we sort of learnt here? Well, we've learnt that we know how to do asynchronous programming, but there lies a question that is that relates to something I mentioned before, which is, I was saying before, threads aren't necessarily like the fundamental unit of asynchronous programming, of concurrent programming. we've sort of probably come to think, like a lot of us in the course might have come to think of them as the fundamental unit. Just because like that's sort of the way the course is structured to make you think about this stuff. But surprisingly, a lot of the time threads might actually be overkill for what we're trying to do. Now, why is that? Well, if we think about this program that we've got here, let's look at what that program might look like visually. So we have a main thread that's like going and executing code, and it goes off and spawns three new threads. Right, 3 new threads. And in this case, in Rust's case here, these are what's known as operating system threads. So these are threads that are literally like genuinely handled by Linux on my machine's case. You know, operating system threads exist on Mac OS 2, they exist on Windows. And so you're actually spawning this real operating system thread, and it comes with a lot of stuff. I'm drawing these as sort of like big boxes, you know, for like diagrammatic effect, but genuinely because a thread usually comes with a lot of data associated with it. So that data might be things like variables that it's got on its stack. They share the same heap, but they have different thread local data that all needs to get potentially spun up and initialized when you're creating a new thread. It has its own sort of idea of where it's at in the program. It has its own registers and stuff if we're talking on a really low level that it wants to like deal with. And Linux is going to have to spend probably a reasonable amount of time switching between these different threads. So let's say I actually really only have one core available on my system. Like my system is really only able to do one thing at a time. It's probably going to have to go, okay, create a thread, create a thread, create a thread. Don't start doing any work on them yet. Just sort of see, okay, there's 3 threads. Then Linux is going to go, all right, main's now saying wait for all of these things here to finish. So I'm going to go and like do some work. It switches from main over here and, you know, does some work, and it says, oh, I'm waiting for Rust-lang org. So it goes, okay, I'll switch to this one. Oh, I'm waiting for C++. Okay, switch to this one. Oh, I'm waiting for Python. We'll switch back maybe to this one. It's still waiting. We sleep for a bit, sleep. Okay, check. Oh, yep, Rust-lang's coming back. So we'll go over here and continue on, and this one. And right, so we're switching between the different threads quite a bit. And eventually we're going to end up coming back to main here and continuing on. So to an operating system, to something like Linux, a thread is really like a sort of its own data structure, right? It's its own unit in a certain sense that is able to that has its own, like, let's say it has its own stack, it has its own registers, it has its own thread locals, it has its own like, you know, position in code that it's executing, right? It's got all these things that make it up, and switching the sort of context of what the computer is performing from one thread to another, right? This switching here is quite literally called a context switch. Can be quite timely, expensive, you know, use up genuine, like, potentially precious resources on the computer, like the time that you have. And if we really deeply think about what we're doing here, like, do we need 4 threads, 4 like Linux operating system threads in order to do what we want here? Do we definitely need 4 threads? And the answer is actually no. You could do this with just 1 thread and still have, and like without a sacrifice in performance, that is to say. Because again, we're not like, it's multiple threads open us up to the possibility for parallelism across cores. So in my case here, if I look at if I open up this top program here, you'll see that my computer has 16 cores available. If I only ever write very sequential code, no matter how smart the computer is, it's not going to be able to take my purely sequential code and run it simultaneously across 8 cores in order to speed it up, right? It's only sequential code, so I can only really take use of one physical core that's capable of executing one thing at a time. So when you use multiple operating system threads, like in our diagram here, you open yourself up to the opportunity for the operating system to truly parallelize your code. And it goes, there's 4 threads going on here. We have the resources available. Let's run it all on 4 cores. And so if your work is quite, heavy on the CPU, needs to crunch a lot of numbers, then you open up the possibility for parallelism to really increase the performance of your code. But for something like this, or for something like an IRC server, let's say, threads are probably like overkill. We don't need all this extra information. Realistically, all we really care about is this is some form of a task. And we can think of this task as something like a state machine. So like these tasks are all basically doing the same thing here. We could make it generic. I just copy pasted the code, but you could imagine we wrote a function or something like that. In fact, that's not that bad an idea to do, because it actually will help demonstrate what I want to say anyway. So if we had a function that was something like get website, let's say, and we have a URL, which is a string, and the name of the website is a string, and this should give back a string, which is the actual response, then we're going to get something like this. Except I guess probably without that one there. So sending request to the name of the website, get the URL, received response from the name of the website, and then give the response back. And then in here we can say get website. The URL was, I shouldn't have deleted it, I'm stupid. I think it was rust-lang.org. I don't think there was anything special about it. And I'll just write rust-lang now. And this should be let response equals. Okay. Right, so does what we've got here roughly make sense? See how that's like analogous to what we were doing before? It's a pretty simple refactor all in all. And here we're just gonna have, we'll say sending request to C++ reference, which is this URL here. Cool. And here we are sending a request to python.org, and here is the URL. Okay, cool. So our code's a little tidier now, which is great. Still some duplication going on, but I'm happy with that. Cargo build and run it. Takes an equal amount of time, 1.2 seconds, whatever. Yeah, something like that. I wonder if this even, let's just see for fun if building with optimizations speeds it up at all. I imagine it might a little bit with inlining the functions potentially, but I mean, you spend all your time waiting for the websites anyway, so I imagine even building with release optimizations is probably not going to change anything. And it is 1.4 seconds this time. Okay, it's just somewhat variable. So, okay. Now, here's why I wanted to do this. Oh, what the heck? Now we have a somewhat generic idea about what this kind of a task looks like. So let's imagine there's sort of 3 parts to like what's going on here. We have sort of, like part 1 here, part 2 here. There's not really 3 parts. I'll just call this like part 3 here, which is the end essentially. Now in part 1, we actually, sorry, no, I do remember why I wanted 3 parts now, because I'm stupid. I wanted a part 2 right here, like that, and then part 3 being the end is sort of like here, actually. Okay. So there's three parts. We've just called the function and nothing's really happened yet. Right? Called the function and we're just like getting ready to start doing everything. Then we call get on this URL, and this function is going to make us wait until the response is ready for us. That's what I'm calling part 2 here. Part 2 is when we fired off the request and we've got nothing to do for now. We've got nothing left to do. And then, in theory, this request comes through at some point, and that moves us on to part 3. Part 3 can really be seen as like right here onwards in a certain sense. Where we're not waiting for anyone anymore. We can just continue on with the rest of our code, and it's going to be microseconds before we're at the end of the function. Like here, maybe like a whole second we're waiting. The rest of this, just microseconds to execute the last little bits of code that we need here. Right? Do we see how this sort of like can vaguely be seen as like these 3 different parts? So to think about this diagrammatically, we sort of have, you can think of this kind of like a state machine. So we have the, what did I call this? Get website. So get website, if we're thinking of it as some kind of asynchronous task, it says like we can sort of initialize a get website task and nothing's really going on yet. Then if we like, let's say this is like, this arrow here means like do work. So we do some work on get website and that initializes us a thing that's ready to make a call. Then we say, all right, do some work. And what's it going to do? It's going to send request to the website. So it's going to ask the website, hey, I'd like to get the information, please. And it has to wait for it to do that. So, you know, this is going to take some amount of time. This is my beautiful clock, you know, icon here. Sends a request, takes some time. And then, you know, eventually when we do some more work, we're hopefully able to spit out some kind of result. Right? The actual response that we've got out of it. And then the task is done effectively. Right. So this is really what we care about in terms of a task. Is there anything that means this needs to be done on another thread? Well, kind of. This part here was the scariest part. This takes a lot of time, right, to actually get the response back. And so we've learned to say, since this call is going to like wait for a while, right, you're going to have to wait for the response to arrive, send it to, like, make sure this is done on another thread so that thread can spend the time waiting. And then when it's done, it gives that value back. But what if this send request, what if we like didn't necessarily wait for it? What if we fired it off? Like what if we said, send the request and I'm not going to sit here waiting for it. I'm not going to be, say, like a thread that is just waiting on this line of code. What if I like return back to whoever's working on this task and say, like, I'm not ready yet. I'm not ready. But I might be soon. Right? I might be soon. Right? So imagine there's someone else here. There's someone else that is trying to get the website. Right? There's someone else here would be function main in this example over here. It wants to get a website and it says, okay, how does it do that? It goes, I'm going to call get website. And that's going to give me, it's going to give me a website here. That website equals this. Cool. So effectively, when I call this something like that, we're going to imagine that we're at this state here. It's been initialized and it's ready to go. Then me on the outside, I'm going to say website.doWork. Right? Website.go do some work. And it's going to do this amount of work, fire off the request to start, and then return back to me. It's going to return back to me here. And it's going to say, I'm not ready yet. And I go, that's fine. No problem. You fired off the request. I appreciate that. I'm going to go do something else. And maybe our code goes and does something else in the meantime. And then eventually it comes back and it goes, all right, let's see where we're at. Website.doWork. And maybe at this point, where that doWork function goes off and checks the state of the request. Has it come back yet? Are we still waiting for something? And it goes, oh, we're still waiting. And maybe it just says, well, like, once again, you know, we're not ready here. But maybe the request has come back and it goes, great. That doWork here is not just going to say, hey, I'm still waiting here. It's going to go do the rest of this and actually give us our result back. So it might give us back ready of the response. And effectively, this task here is done. So this is a slightly different way of thinking about how to work concurrently without using like operating system threads like we've been doing in the rest of the course. If you can like vaguely understand how a system designed like this, right? Not a system based upon spawning threads and stuff, but a system designed around doing this kind of thing, how that might exist, then you're starting to understand Async Rust. Because this is effectively how Async Rust works. Now there's some more details that we're going to play around with. But it's effectively how it works. Okay. So let me check the chat then. x86 stocks would take forever. Yeah. Firing up a thread takes time, means your process needs to deal with multiple CPU cores. Wouldn't it be nice if in cases where we're just waiting rather than processing, we could do the waiting on the one thread? Yes, exactly. So instead of having, and I mean, the case that we've probably got right now is that main fires off these 3 threads. They all fire off their request, waiting. Fire off request, waiting. Fire off request, waiting. And main is also like waiting for the 3 threads. For probably like a whole second, we've got all 4 operating system threads that exist just to be doing nothing. They are existing just to sit and wait. And then eventually when these requests come back, they continue on, and then main wakes up and does its stuff. When really, we could have done all of this just on the main thread. Like if everyone's main could have just gone with this task model, you know, do the website, do that website, do that website. Main could do the waiting until the websites are all finished, and then you know, print out the results or finish off, do whatever it wants to do. So we're starting to think in this sort of task-based model here. This task-based model here. Okay. 1521 moment. Yes. Low-level things be fun. And my quad core getting flexed on real hard right now. Okay. So the interesting thing, actually, let's have a quick look at Rust for a second. I think we're getting bored of the diagram a little bit. Oops, I clicked the wrong thing, but that's fine. So this idea of a task. Oops, don't do that. This idea of a task in Rust, we call this future. This is future. Now, future is a trait. Kind of, it's maybe helpful to sort of think of it in the same way that you think about iterator. So future is a trait. It defines a type output, similarly to how iterators define a type item, which says that the type that the future is hoping to eventually produce. And it only defines this one function here called poll. Poll is the translation of do work in our example here. So do work is what we call poll. And this overall idea that I was calling like a task up here is actually a future. Right. Now the poll type here, like what the function poll returns, poll of self output, guess what? It's just this. Poll of t is either ready with that t or it's pending, right? That ready and not ready from this is just this poll type here, which is, we would call this isomorphic to option, which essentially is to say poll of t behaves the exact same way as option of t does. well, yeah, essentially in that you can convert between, say, poles of t's and options of t's with no loss of information either way. They're basically like the same thing, is the very sort of simplified way to see it. So if you look at this and go, look, that looks like an option, it basically is like an option, but it's they use a separate type to sort of signal intent a little better. Option maybe looks like there is nothing, right? If it returns none, that there will never be something, whereas poll calls the none in this case pending, which sort of implies that it might, it's probably going to arrive at some point, it's just not there yet. So poll takes self, and it takes self as a pin of ref mute self. I have no idea if we'll end up having time either today or tomorrow to talk about what pin means, but essentially you can imagine this takes in self, or you can imagine it almost takes in a ref mute of self in a similar way to how, say, an iterator, the next function takes in a ref mute self, right? So poll really looks a lot like next on an iterator, excuse me. It takes in a ref mute self. It also takes in a context. Now this context currently in Rust, it only holds a waker, which is another struct that we'll talk about later. It's called, like, why don't they just pass a waker then if it's just going to be, if that's all it ends up holding? It's because they might want to put more stuff in the context in future, but nothing's really made the cut yet other than a waker. So this context here really just exists to hold something called a waker, which we'll also talk about later on. And poll effectively just says, am I ready with a value, or are we still pending? Are we, still waiting for the value? Okay, cool. So it's okay. It's 7:15. Let's take a break for a bit. But yeah, that's where we're at right now. We've just talked about this different idea of thinking about. Oh, actually, no. Okay, there's one more thing I want to talk about before we go to the break. Which is that this sort of abstraction for thinking about asynchronous, like the idea of asynchronous programming, I would argue is more flexible, more generic than threads. The reason I would say this is more generic or more flexible than threads is because you can implement a future by using threads. So what do I mean by that? Imagine we have a type foo, struct foo here, and we want to implement future future for foo, where why am I calling it foo? I should call this like website request, something like that, where the type output is going to be the string response, and poll looks something like this, but it doesn't import anything because it sucks. And you could write something like this. You could say we have a channel is a std sync MPSC receiver of a string. Like this. I don't know. Why am I not importing anything? Let's grab this. And then that. So we have our receiver is this. Okay, that's fine. And we can say something like, okay, sorry, I'm gonna have to rewrite this. Bear with me for a second. Enum website request, sort of init I mentioned, and then sent request, and then I want this, and then request done, like that. Okay, cool. So website request of these three things, we can say match when someone says, hey, I would like to do some work on the website request future, then we can have a look at like, what do we currently look like? We'll Rust, oops, that's not what I want to do. Rust Analyzer will help us out here. Thank you. Like so. Like that. And we can write some code that looks like this. So where are we currently at? If we've been initialized, okay, it's got to stop with the errors. Please stop with the errors. Okay. Okay, yes. Let's go. Yeah, that's probably fine. Okay. So if like we're in this sort of a init stage, which is part 1 here, we need to send that request. So I can write some code that looks like this. Let sender receiver equals mpsc channel and spawn a new thread. Std thread spawn a move closure. Which does what? It does this. This bit here. Like so. So actually go ahead and get that URL. We also need to know the URL here. So init maybe has a URL we have a URL here. Init with a URL here. We move the URL in. There we go. We've got a URL in there. And you're upset because sure, that should be fine. But okay, it doesn't know what the channel is yet. We've got a response, and then say sender.send response. All right. Now the compiler is going to be pissed off, probably because oh boy, this is getting too big. Let me just do a big error. It doesn't like that. Let's double check here. Match self.deref, and it sees that self escapes these lifetimes are really hard to see here because it's slightly too big. It doesn't like that we have self here and then this lifetime. Yeah, we're having fun here naturally. So when you're trying to write this really low level async code, it gets particularly fun. And I want to just like, in fact, let me write some code during the break because that's going to be more productive. Also, where'd the arrow go? Okay, there it is. That's going to be a little more productive. We'll come back in 5 minutes when I have something to point at, and that'll probably be a little more helpful. Debugging, having fun with async Rust shenanigans in front of a live thing is lots of fun naturally. So let's take a 5-minute break or so. I'm going to write some code during the break. We'll come back and I'll be like, here's how this is sort of equivalent to that, and we'll talk about what that means in a bit. So let's have a quick break. All right, let's get back into it. Give me one sec. All right. Okay, so back to this. There we go. The issue was very quick to figure out. By the way, I knew I was doing some horrible crimes with the URL, and so I just cleaned up the code a little bit, and the horrible error that wasn't particularly descriptive, at least for me, managed to disappear. We're coming back and we've got a whole bunch of code going on here. And this is what I want to sort of look at for a second here. So imagine we think about our website request in terms of this state machine here that we're talking about, where there's 3 states. The initial state, once we've sent the request, and like once we're done. Right, so in our case, we can, so if someone wants to make a website request, they can generate a new website request in it, or like you can imagine this like ready to make request with a URL. Then, in theory, we should send off that request and then say we've sent the request and we're waiting to get the result back, get the response back. And then once like we've done some work again and the request is done, nothing more to see here. And this poll function, like this do work function, can look something like this, where it says, if we are in the, like when we want to do work, if we're in the initial state, we haven't done anything yet, create a new channel, right? Channel to just send and receive, and spawn a thread. So, right, the thread's coming back into this. This is coming to my argument where I'm saying I think that futures are more generic than threads, because we can implement a future by using a thread as like the implementation. So our thread says, make that blocking call, request blocking, get that URL, blah, blah, blah. And then once we've got it, send that response to the sender. Sorry, send that response through the sender such that it can be received on the other end of the channel. So we fire up this thread to go do this work. And then we say we are now, like star self equals, we are now in the sent request state here, where we have this receiver, right? This receiving end of the channel that we're waiting to hear the result back on. But it's still not ready. So we give back poll pending for now. Then if they call like poll again, like try and do some work, they'll go into this branch because that's what we're in here, sent request. They go into this branch and we'll call receiver try receive, noting that try receive in particular is not blocking. It'll never block the caller. It'll just see if it's there or not. If it is there, then great, request done. So we update ourselves to be in this state here. The request is now done. And we give back poll ready. We say, great, the response is ready. Here it is, and give it back to them. If there's nothing in the channel just yet, then we'll just say we're still waiting. And then theoretically, once they get this poll ready with the response here, out of this, once we're in the sent request state, they should be happy. They shouldn't need to use the future anymore, but they technically can if they want, in which case the request is already done. And so probably we just want to say something like panic and say like the request was already completed. And so now we've built up, like using a thread sort of as our backing implementation here, we've adapted what we've done into this new task system. So we still haven't used anything to do with this context here. But so we've got the get website function, which just uses, in fact, we should imagine that this function maybe like spawns a thread and does that stuff, whatever. But get website future, we can imagine doing a similar thing if we create a new website request with this URL. We construct a pin out of that, which again, we're not talking about just yet, which is our future. And then we're almost ready to call future poll, except we need to pass it a context. What we're doing here right now is like pretty esoteric. it's pretty like, this is not the usual way you would write async code in Rust, and it's more to demonstrate how things work. So I'm going to make a, like if we have a look at context, in order to create a context, you need to provide a waker. And a waker, we can say, where is what I'm looking for here? There should be a constructing a waker, well, making your own waker essentially. Where has this gone? Waker. From raw, no. Wake. Traits wake. Let's see. This trait can be used to create, right, sorry, right. So this trait, we should be able to make a waker. Sorry, it's been a while since I've played around with this stuff. Impl this, and then context from waker. And that context from waker. Does this not take in, I must have misread this. Context from waker takes in, let's look at the source quickly. That's strange. It doesn't seem like that should work, but all right, we'll trust the documentation. Great. So we're just like, we're not really using this anyway, so I just want to steal something, and we'll talk about wakers more generally. And in fact, no, I don't even want this really. Wake, just do nothing. We'll call this our waker. We'll call this our waker. Impl wake. Arc. Impl that. Great. And it just does literally nothing because we're not using it anyway. And then waker is arc new of this, and apparently that should work for us. Oh, dot into. Ah, that's what I was missing. Right. There probably is where there must be on waker here. There must be from arc of W. That's it. That's the implementation I was missing here. Right. I mean, you're not going to memorize the whole standard library in your head, and that's definitely being proven true from what we're seeing with me right now. So create a new waker, and then finally we can call future poll with our dodgy waker here that doesn't actually do anything. Our waker. All right. What are you pissed off about? Sorry, that should be waker is this. Let context equals context from waker, takes in a borrow of waker, and finally we're ready hopefully to call this with ref mute context, which means that this here needs to be mute, and that should be great. We're compiling. Okay, so a whole bunch of cruft in order to like cruft that's sort of useful to be there, and we'll see how much of it we can really talk about. But in order to poll our future, and I could just do something like this. I could just say while, or let's say in a loop, call future.poll. Right, call future.poll. Let poll equal future.poll. Match on the poll. This will return a string eventually. Match on the poll. If it's ready, if it's ready with the response, then give back, like let's actually return that response. If it's pending, then we'll just do nothing, like that. Where is it getting moved? Future dot use of move value. Poll should, no, future's in a pin. Do I need to use the unified syntax? Oh, Right. Yes. I probably need to. Yeah. So I probably need to write. Why don't we just try pinning it each time? Like this. Again, this is really just not relevant to what we care about here today. And yeah, okay, it's happy, cool. So we say essentially poll our request, and then hopefully when it's ready, we can return this response. Now, this should so far be feeling like a little bit dumb, what we're doing here. But I promise there's a decent payoff to this in the end. There's sort of like a, oh, I see why why this might actually be useful in a bit. Okay, so now we've written a slightly different alternative here, where we're still sort of going to be spinning in a loop here, asking the poll, is it ready yet? Is it ready yet? Is it ready yet? So this overall function is still going to be blocking. It's still going to block and wait for this string. But you'll notice that each time we call poll on our future, this poll here is not really going to ever block. It's just going to say, it's just going to be either it's here or I've fired off the request, but I'm it'll never end up waiting for a whole second here. It's just going to tell me if it's ready or not right now. And we're blocking over it by looping over this thing a billion times. So in theory, we should be able to swap get website here for get website with a future. Get website with a future. And this in theory should act much the same way. Potentially just slower right now, the way we've written it. Yeah, so slower, but it still ends up doing the same thing. And maybe it's in fact, it's even barely slower in a small example like this. Yeah, it's essentially even the same speed. So that's quite interesting. Okay, so this is what we've got now. Forgetting all this cruft at the top here, where essentially we're making a website request, starting off with init URL, and we're saying poll it, poll it, poll it, poll it, and this poll function will always be very quick to call. It'll never end up waiting for a while, and it'll eventually be hey, I'm ready, here's a response, or it'll be I'm still pending, right? It's not quite ready yet. And then the way we've written this up here is sort of like a state machine, as we were talking in this diagram here. We're saying where we are we haven't made the request yet, you've just sort of initialized the future. We've actually sent the request and we're waiting to hear back, and we've actually heard back. And then we look at the state that we're in right now and either fire off a task and, or check on the status of the task, and then eventually, we're done, and we sort of transition through the state machine by saying, now we're at this point, now we're at this point, hey, we've already finished, you're doing something wrong. Why wouldn't the poll notify the get website future when it is ready so we don't need to check in a loop? That is a fantastic question. That's so good. So let me I'm gonna come back to that in a second, but let me just sort of make some bits and pieces clear here. This premise of a future trait, right? The impl future for this in this sort of interface and stuff worked even when all we want to use is a thread. It for some value of worked here. The work is implying that, I had my own fun and pain with waking and pin and lifetimes and stuff. It's maybe not easy to write, but it's written, it works, it does the same thing, but it's under this generic interface of future now. Why is that something that we care about? Well, now with future, right? So a task that I might want to do in a thread is applicable to a future. A future can now sort of represent the idea of a task that can make progress over time. It's almost if you can almost think of a future also like a generator. if you've used generators in another language, like say Python with yield and stuff like that, a future almost acts like a generator in that kind of way, where you can say call it, call it, call it, and it'll make a little bit of progress each time. Or like in our case with a future, it might make no progress. It might just be like, there's nothing to do right now. I'm just stuck waiting. But eventually, you know, with a future, it's going to say, it'll transition sort of through the state machine and then eventually hopefully say, hey, it's ready. So that's kind of cool. That's like, this has now offered us a generic interface, right? A generic interface to talk about the idea of a task that can be executed kind of concurrently. You can imagine that like this, the way I've written this kind of sucks here. Imagine I had, this is gonna kind of suck to write. Can we still do it regardless? I'm gonna quickly try, and if it doesn't work out easily, then I'm just going to like undo for a while. You can imagine that I can write something like this. Websites is a slice of the URLs and the names of them. We say let tasks equals vecbang. Or even let's say websites dot into iter dot hello. Where is I forgot the tuple friends here. Tasks dot into iter dot map the URL and the name to let's say println sending request to name, website request init URL. In fact, this println doesn't really make a lot of sense anymore. Yeah, I guess just map it into that. Dot collect. Yes. Then we don't need this. We keep our Waker and our context that we're just going to share across all of them because we don't use them anyway. And then in our loop here, we say for task in tasks.iterMut, like that, which it doesn't, collect, sorry, into a vec, I should say. For task in tasks.iterMut, do this. Where this is task, which is already a ref mute with the context, and then something like this. Okay, so this is not quite going to work because it's just going to return the response from the first like task that it sees. But there's something to this in that this function can now take a list of websites, like a whole sequence of websites, and start to work on them all somewhat simultaneously. Now the code here that would actually grab all the responses is probably going to be something like, I could write something really janky right now, which is just like responses is a vecbang, and then we say something like, let's even map this into the task and the name. This here says for task name. Then we say if it's ready, responses dot push task name. I'm gonna have to get rid of the panic here. Like this is probably good, but just to save myself from writing things, I'm just gonna make this return poll pending afterwards. And then just go loop if responses.len is equal to tasks.len, then break. And at the very end here, give back responses like this. And this is going to give back a vec of the task names and the strings. and it's going to get pissed off about the lifetimes, but that's fine. Tick name. This here is tick name, and this here is tick name. And then it should be fine. Or I got them backwards, I guess. Oh, yeah. Yeah, this should be name response. Yeah, thank you. Yes, you all seem to have figured that out. And then it's upset that I have name is a at mute at stir. Okay, yeah. So probably 2 of these. And Bob's your uncle. Great. So now we have an interface that can deal with all these different things, like all these different websites being sort of worked on simultaneously. Now, why is this something that's potentially kind of cool? Well, if we say get website future, our website is going to be a vec of these 3 here. Let responses is this. Println responses like that. And the websites are going to be, God, I hope they're this way around. URL name, and URL name. Like that. Is it URL name? Yeah, that's URL there. Great. Cool. And the code seems to compile. So we can write something like this. Let's see if it works quickly. Because honestly, it might not. You never know. Yep, that seems to work. It's just spitting out the responses as these horrible strings here. But you can see here it goes, yeah, Python.org is this thing, and there's probably C++ and Rust and stuff at some point as well. And it's taking approximately the same amount of time again, 0.933 seconds. Here, so this is kind of cool. This seems to generally work. Here is the insanely, stream suffer? It seems happy. Stream health? Stream is healthy. Oh, but everyone's, is it back now? Or is it okay? Good for me. Rip stream? It's okay now? Okay. That's weird. I didn't see anything on my end. It looks, even YouTube's the first one to complain. YouTube's like, yeah, it's great. Okay. All right. Seems fine now. Cool. So the really interesting thing about this is that notice nowhere in the code that is dealing with like all these different tasks here is there a thread spawn. There's no extra threads apart from the thread we're working on in like the code here that's dealing with many things at once. Right now it's just a loop that's going over each of the tasks, right? A loop that's checking on the status of the tasks. If you're familiar with, say, something like JavaScript or something like that, this might be starting to ring some bells. A loop that's checking on the status of each task and potentially making progress on them, like little bit by bit as well. That's interesting. This is all just done over a single thread. Now, you might go, well, Zach, this like, sure, you can claim that, but like scroll up here. This is still using, you're still using the threads here. In fact, you're still using the same amount of threads as we were at the beginning of the lecture. And yes, you have got me there. That's true, the way I've written it right now. But remember, this thread here, right before what we had at the beginning of the lecture, those threads were fundamental to what we were trying to do, right? They were fundamental to allow us to even think about the idea of multiple tasks happening concurrently. Now it's an implementation detail up here. Now it's just like, in order to get the response from the website, we use this, blocking thing here. But like, it doesn't actually have to be a thread. This is the really interesting thing. What if we were able to say, send a request off to a website and like, don't make me wait until it's done. Just like send it off and I'll make some progress. I'll check on it every now and then, right? That's a future. A future is like, do a little bit of work at a time, just a tiny little bit with no blocking, and you know, I'll check on you and see how you're going. And if we look at request, we'll find that the standard interface for using request, there it is, gives back a annoying asshole is async fun. This basically, let me desugar this. We haven't actually looked at the words async or await yet, but this, the signature for their function is basically this. In fact, it's exactly this. It's when you want to get a URL, I'll give you back a future that eventually should hopefully give back a result of response. And there are, like, not on every system, not necessarily every system, but most modern operating systems these days, there are tools to tell the operating system that you'd like to fire off a request to a website, but like, I'm not going to sit here and wait. Just notify me, tell me when the response is back, right? Tell me when the response is back. And so using that, you can actually work on get a whole bunch of websites simultaneously, you know, concurrently, with just one thread. Right? That's kind of cool. So you can even imagine, gosh, I don't know if I can try and see if I can type this quickly, but like, we could have sent request here be a boxed-in future where the output is request result of... Oh, YouTube seems upset, but my end seems fine. 0 drop frames. Where was I? Of response. Request response, like this. And then this here, instead of... I think this is YouTube's fault, honestly. Like, I know I shouldn't be blaming YouTube, but like, everything's fine on my end. Anyway, I think it's just buffering every now and then, so you might just need to go 10 seconds back or something. Oh, okay, I see my network dropping down for a second there. Okay, well, maybe it's my fault. Just go back 10 seconds or so, and it should be okay. It's not... Okay, I've dropped like... Okay, I have dropped a few frames now. I think it'll be fine. We'll tough it out for the next few minutes. In fact, I'm just gonna write this code anyway, so it's whatever. Request get URL star self equals self sent request of request get URL. This is gonna be a box new of this. Which it seems happy with. Yes, cool. And then this over here, we can just go, instead of matching on receiver try receive, we can say match on, here should be the request future dot poll, which it's going to be pissed off about because it's boxed in future. We might, yeah, because I'm gonna have to throw a pin in here, which is annoying. I can do is it unpin? This is okay. This is gonna tell us if this is gonna be horrible or not. So that's just a result. So I need to check this, and I need to check this. Is this going to... Okay, this is unpinned, so this is fine. Is this unpinned? Okay, this is actually going to be fine. It should be relatively easy. So let pin be pin new of request future dot deref mute this. This needs to now be deref mute, which fine. Cool. cannot be unpinned. Consider using box pin. Yeah, it's not gonna. It doesn't see the type of it anymore. Could I just store? No, because I can't name the type. Yeah, this is gonna suck. Okay, this is not happening. Today at least. But you know, sorry. Yeah, this is gonna be too painful. I can maybe do it after the lecture and tell you about it. But what I mean to say here is that this code here, right? We could leverage essentially what request, the future that request gives back, which probably works, you know, just on the current thread. And when we sent the request, just check, like instead of checking on the receiver, we would just match on request future dot poll with our same context. And if it's ready with some sort of response, then we can do this code here. And if it's otherwise, if it's pending still, then we're pending still. Right? So essentially what this is giving us is a way to compose concurrent operations within each other as well. Right? So it's letting us compose async operations, and also is potentially helping us eliminate the need for threads at all, and just sort of, you know, make work on all these operations over like a single actual thread, which is very interesting. Now, Rust is, again, at the end of the day, a relatively low-level language. You know, largely in part that they want to support low-level programs and they want to be able to have extremely high performance. So writing this code itself is like, can be really nasty, as we're seeing here. I'm going to go back a little bit just to where we still had a working program using threads, which would be here. But like, this is probably all we need to like think about in order to understand how the system works, such that we're able to like use it relatively effectively, which I think we can do on Wednesday. So this was like sort of a peek beneath the curtains in terms of how future itself works, how we can think of concurrent operations as sort of transitioning through a state machine, right? Where each time we're just sort of like either doing a bit of work and moving a step in the state machine, or just saying like, hey, things aren't ready yet, and returning this poll pending. And then using this future to sort of work on operations, work on tasks concurrently without necessarily needing threads as our core primitive, to do tasks concurrently. So some things that we can talk about on Wednesday is, first of all, like getting rid of all of this crap here and just writing high-level Rust code using async, the async keyword and the await keyword, which essentially mean that we don't have to write this stuff here manually. We don't have to write any of this stuff here manually. Essentially, the compiler ends up generating all this code and this code here for us just by writing something like function website request, takes in a URL, is a static stir. We'd say it's async and it gives back a string, right? So this will generate, it'll do impl future. It'll like essentially turn our code here into this, returns something that implements future that will hopefully eventually output a string. Like that. That's what it'll turn us into there. And then we can just write, like, instead of writing this whole state machine and everything, we can simply say like request get the URL dot await. So like this dot await here, request get URL returns a future, and we're saying until this future is done, we're just gonna like delegate away to that future that here, and it'll generate a new enum variant for us like this, saying, hey, this is for the point that we're waiting on this future here. So we'd say like await it. Then once it's there, we'll unwrap it. .text. Unwrap. Text. Oh, text is also an await point apparently, because this might block or might take some time in order to do. So we say throw that behind an await as well, so it'll generate another variant and all this code in here to do all that sort of stuff. And there, this is what our code ends up turning into, and the compiler does the rest for us. So we'll write some actual code with async await next lecture on Wednesday, and we'll also talk a little bit about this context that we didn't use at all, because I ignored a question earlier, which was, why wouldn't the poll notify the get website future when it is ready so we don't need to check in a loop? And the answer is yeah, absolutely, we don't need to do this checking in a loop. And actual like event loops that we'll look at on Wednesday that do this operation, looking at for tasks and making progress on them and stuff, don't just randomly do it in a loop endlessly. Because that's just a waste of performance when we only need to say like poll a task when the task is ready to make some progress. And that's what this whole context, which just wraps a waker. So that's really what this idea of a waker is all about. And we'll talk about that on Wednesday as well, because wakers, even though our waker is horrible, wakers in general are actually pretty cool. Okay, what are we talking about? We're surrounded by blue skies and calm seas. Can you explain what the poll function is doing again? So is a future just abstracting the idea that a task might take some time? Yeah, essentially. A future, there's a couple different parts to like what makes a future like really a future. If you're looking like on the really sort of bare bones level, like a future is just this, right? In the same sense that an iterator is just a thing that defines some item type and has a next function that can give you back an option of that item. Like, it's not usually convenient to think of things in this bare bones way, because like you could imagine implementing an iterator that every second time you call it gives back none, and the other, you know, the odd times it gives none and the even times it gives sum of 42, right? That's technically an iterator, just not a particularly useful one. So how do we usually see futures? We generally see futures as some kind of state machine. So something that needs to perform certain tasks, right? Tasks especially that may wait, that may need to wait for something to complete in order to eventually complete themselves. And it provides a way for a future, for something that implements future, to give control back to the thing that's asking for it to perform work when it's stuck waiting for something else, when it doesn't have anything particularly good to do. So in our case here, when they say do some work when we're in the initial state, it's going to fire off a thread to start start working on that web request, and then just give control back. It's going to give control back to whoever is calling poll in the future and say, I'm done for now. That's all I need for now. So I guess I don't see the advantage of this over just spawning and joining a thread. And the way we've written it right now, there isn't really that much of an advantage to just spawning and joining a thread. The two really convenient things about futures in Rust, well, maybe even three potentially, I don't know, two, we'll see, is things that I quite like about futures personally is one, I find them to be far more composable. So by composable, I mean I have some asynchronous task that I would like to perform, which relies on, say, 3 other asynchronous tasks to be performed as well. In a thread system, you end up having to like write additional code, like with, say, channels, or with, say, like a mutex or something like that, in order to communicate between a thread that's saying that, like, I'm going to go do some other stuff and check on this periodically. That idea of a thread communicating to you that, hey, it's not ready yet, maybe it's a channel that doesn't have anything in it yet, or it is ready, and like here's the results, here's the fruits of my labor, here's the result of my computation, is really this core abstraction that a future provides. And because we've got this core interface of a future, it means that any kind of task that might involve waiting for something to occur can all be thought of under, can all be sort of used under this one generic interface. It's sort of like, not to like misphrase you or something or anything, but like saying something like I don't see the advantage of just spawning and joining a thread is sort of similar to like I don't see the advantage of the iterator trait when I have vec, right? And it's like, sure, most of the time you could just spawn and join a thread, but what if you don't want to use a thread? Or what if you don't have threads? Or what if the threads are causing like a big stall in performance for your application? Like imagine your IRC server. I've heard of a lot of designs where people are spawning 1, 2, 3 threads or whatever for each person that joins. 10,000 people sit idly on your IRC server and suddenly you have 30,000 threads just sort of sitting there doing nothing, right? And each thread, this comes back to like this point here, like has a lot of stuff that it needs to think about, and also places like puts load on the operating system in order to think about them all simultaneously. The great thing with futures is that they don't necessarily need threads to back them up. And when they're like sleeping, when they're not really making progress, there is an incredibly low cost to storing a future. Like if we think about where I've actually stored my futures, I create futures over here, right? I create them over here and then I like mutate them through this. How much space is each future going to take up? Well, I know I am using threads in the back end here, but again, implementation detail, we could take the threads out of this. So how much space is it going to take up? It's going to just take up whatever the most expensive variant of this is. Right now, it's probably this channel, but you could imagine this future taking up 8 bytes, 16 bytes, 32 bytes, something like that. Whereas a thread might be like genuinely a lot of resources, even if it's just existing simply to sleep. So it's this very interesting abstraction over the idea of a concurrent task, an asynchronous computation. And no matter what this computation is predicated upon, it might be like the asynchronous here might be I'm waiting for a website, or it might be I'm waiting to read a file, or it might even be something like I am waiting for some duration of time. Like I'm sure everyone at some point has written something in their code that's like, say, doing stood thread sleep for sleep milliseconds, 1,000 milliseconds, right? This could be a future as well, which is just like say pending, like give back pending for the first 1,000 milliseconds, and then once a second has passed, then you can give back poll ready, right? So it's a sort of level up on what we're able to do, how we're able to represent concurrent computations without necessarily needing threads. You can still use threads all you want, and lots of futures may be implemented with a thread behind them, right? So it's not like we're losing threads by using futures. It's just that you can pick and choose when you actually want or need a thread. And so you only need to like pay for what you need essentially, which is kind of cool. And then, yeah, the composability is also potentially a really big win as well, in that if like a thread threads are kind of poorly composable construct, in that if I have 5 different tasks and the way I talk about a task that I need to complete is with a thread, I generally have to write a lot of multi-threaded code and think about things like send and sync and all the pain that comes along with that, and how do I communicate between these different threads, like we were doing. I guess we were using thread scope before, which was a pretty easy way of doing that, but without thread scope it probably would have been a bit of a pain to get them to talk to main. And so yeah, sometimes that can be particularly gnarly, whereas composing futures in the sort of normal developer circumstance can usually actually be quite easy. Easy, convenient, and generic, essentially. How do you do it without a thread? Something like a web request. I'm not entirely, like, I'm not amazing with low-level Linux in particular, but I believe you can you could do something like a web request without an extra OS thread in your program with something like epoll, which is an event polling system call, where you essentially say, so you probably still will need a thread, right? In that you need to tell the operating system, wake me up when this web request comes back. But the trick is that you would be able to do, say, 1,000 web requests all with one thread. Or you might be able to do, say, 1,000 file reads all with just one thread dedicated to that. Whereas if your fundamental unit for concurrency is a thread, right? Oh my gosh. Yeah. Okay, it's back now. Yeah. Why is it going up to 15,000 bit rate? It's like a roller coaster. Okay. Can you still, you might not be able to see the screen, but are you able to still hear me okay? Yeah, there's an async poll joke here somewhere for sure. Anyway, what I was gonna say, and I'll say it to the void if need be, but if your fundamental unit for an asynchronous computation is a thread, then anytime you want to do an asynchronous computation, you need to make a thread. If your fundamental unit for asynchronous computation is more generic than a thread, it's something like a future, then you could potentially multiplex thousands of futures onto one actual thread, which is essentially what things like Tokyo, like we're going to see on Wednesday, ends up doing, which is pretty cool. Okay. Yeah, I think... oh, man. Yeah, this is... the bit rate is on a real roller coaster right now. That's pretty cool. Real up and down. That's so strange. I'm gonna have to maybe debug that. But I think we'll call it there. If you have any questions, and I'd love to hear questions as well about, talking about Async Rust, then throw them on the forum, or you can try and get whatever you can out in the chat right now. But yeah, in fact, you can even see here with Tokyo, it says a runtime for executing asynchronous code, including a task scheduler, an IO driver backed by the operating system's event queue, e.g. epoll here. So, yeah, epoll's pretty cool. It essentially lets you go fire off a whole bunch of web requests and then say, put my thread to sleep, but wake me up if any of these web requests come back, for example. And when you wake me back up, tell me which ones are done. And that's what we'll end up using with when we talk about wakers and stuff like that. I've used poll for highway interrupts, but not epoll. Okay, cool. Yeah, I think poll is somewhat deprecated, I want to say, in favor of epoll. Nope, that's not what I wanted. It is meant to replace the older POSIX select and poll2 system calls. There you go. Anyway, there's lots of fun stuff there to gnaw at. But yeah, that's what I wanted for this lecture. Just to be clear, the outcome that I was hoping for this lecture is we've been thinking of our fundamental unit for concurrency as threads threads don't actually need to be the fundamental unit of concurrency. Instead, Rust has defined this generic trait future, which represents some kind of computation, some kind of asynchronous computation that might not have finished computing yet, that you can make progress on and should generally never block, should just like do its work in the background. And using this generic future trait, we can now compose together many asynchronous computations, right? We can compose together many futures, which we're going to be spending time doing on Wednesday and playing around with some actual like user level code, probably after just talking about waking first, because waking is pretty interesting. And yeah, that's, if you can understand that vaguely and like how someone might roughly want to implement a future, in that a very common pattern here is something like a state machine, where like, where are we up to in the computation? And then doing work and telling you pending, or like, okay, it's actually ready. If you can understand all of that, then you're ready for Wednesday. That's basically it. I would have thought it'd do the sending the request bit in the initial call, then you'd wait for the response, which might, when you get to the await bit, I suppose that's more limited though. Yes, actually, that's actually a really nice, interesting point. By the way, if you're, it's 8:25 now, so you can feel free to dip anytime. That's, none of this is accessible anyway, so you don't really have to come regardless, but I'll just answer questions as long as we've got them now. This is really interesting because in a language like JavaScript, when you create a promise here being the rough equivalent of future in Rust, as soon as you create the promise, which is like here, when we create the future here in Rust, it starts working. It starts doing work. And then when you say await some promise, it'll just sit there and wait until it's it's poll ready. That's not how Rust works, actually. Rust, because Rust doesn't like bake this in as kind of like a how do I say? Rust doesn't bake in the execution of futures into the language, right? Like, the future trait isn't some special thing in Rust where when you create a type that implements future, it automatically just starts working on it. Instead, it's just a normal trait like anyone else might use. Like, you could define the future trait yourself just by like copy pasting the definition of it. Like, I could create future like that. There it is. Now we've got a future trait. And so instead, the way Rust has decided to model it is that you just do your little bit of work that you need to do in order to either be finished or just till the next point that you're going to have to wait when poll is called. And the thing that ends up calling poll to get you to do that little bit of work until, to do some work, is your overall executor, your overall sort of like event loop. If you're familiar with JavaScript, your overall sort of event loop executor, which in our case, we're going to use one called Tokyo. But in Rust, you can make your own executor if you wanted. Another really popular one is Async Stud. And I believe Async Stud has an executor. Examples, yes, here it is. Async Stud main. And so then this sort of defines your own executor, which will go off and, decide which futures to poll and when, and sort of orchestrate the overall like running of your asynchronous application, which is also very cool. The thing, like the big brain thing that I'll big brain it again on Wednesday. But the really important thing is that we've written this stuff ourselves here, like doing a web request or something like that with a thread. But the real trick here is that if I'm, say, reading a file, instead of spawning a thread and, going the standard library, like reading from the standard library file or something like that, I can instead use Tokyo, right? Their version of a file, which will, when you say something like read or, create a file or whatever, open, read to end, whatever, it will give back futures that Tokyo knows how to execute really efficiently, really quickly. And so it doesn't end up using, it probably won't end up using a thread at all. Or it'll just have one thread that it does essentially everything on. And yeah, they've essentially done all the hard work in doing this. Open async function open. We're gonna asyncify. Yes. Anyway, we'll talk about this all on Wednesday, I'm sure. So calling poll advances it to the next step. Yes, as long as so if I spam, what we're doing right now is like when we've sent the request, we're spam calling poll, and it's just going like error, 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 error. Like it's not there yet, it's not there yet, it's not there yet. But we don't necessarily have to do that. We could just wait until it says, hey, I'm ready to be called again, which is actually how the system actually ends up working. And then calling poll will essentially always advance it to the next step. There are edge cases where it might go, something went wrong and I'm not ready to be advanced to the next step, and it'll just give you back a poll pending. But almost always when a future says, hey, I'm ready to be polled, and you poll the future, it just advances it to the next step, which in this scenario here, because we're defining a future here using async and await, moving to the next step just means moving to the next await, which is really cool as well. So it just means like we do this work here and then await. And so we wait for this to finish, so control goes back. This is almost like a return right here. In fact, we will return from this function right here, and the execute will go do some other stuff. When this future signals that it's ready to go again, it'll poll us again, and we'll move all the way down to here, return back, executor does some other stuff. Eventually we're ready, and we go, hey, we're ready to be polled again, and the executor goes and finishes it off with another poll. So poll, poll, and then poll is how we end up working our way through this future here with an async function. And you can see here, like, it really doesn't look all that bad once we've gotten away, taken away all this really heavy future state machine stuff. Writing async functions as a Rust developer is meant to be very easy. And again, the fact that we're able to compose all these different kinds of operations and say, hey, we're waiting for this output and then waiting for that output and so on and so forth is really kind of nice. And Tokyo in particular, for example, will offer all kinds of primitives for things like this thing here, like the macro select, which we can say, this is sort of like promise race, I believe is what it's called in JavaScript, which just goes like fire up a whole bunch of async tasks and tell me when like the first one's finished, for example. Or you can have a whole bunch of async tasks and just go, let me operate on their results as they come available. And again, so just composing asynchronous operations becomes so much easier once there's a common interface for everyone to talk about asynchronous computations with, being the future trait, that is. Cool. That would be cool for choosing things like the faster server. Yeah. I've done this before. I'm actually, this is kind of funny. Man, I don't know if this code is still in production. You'd hope not. But I remember writing some code a few years ago that was along the lines of there was this API we needed to call, and the API was idempotent, which means that calling it one time is the same as calling it 20 times. So, for example, an operation that would not be idempotent is something like posting a comment, let's say. I mean, you could make it idempotent, but like generally, if you call comment post 20 times, you'll end up with 20 comments that all maybe say the same thing. Whereas maybe something like editing a comment is idempotent because you're just editing that same comment to have the same contents every time. You edit it once, it's the same as editing it with that same text 100 times, let's say. So the API we needed to call was idempotent, meaning we can, if calling it once is going to produce the same effect as calling it, say, 1,000 times. And this API would fail like 20% of the time. Something like that. It would just fail, and there was no way to know. It would take like 5 seconds to respond, and it would just sometimes be like, it didn't work out, like 20% of the time. And so you could just go in a loop. Just go like, try it until it succeeds. And 80% of the time it'll be fine, but then 20% of the time it'll need to wait 10 seconds, right? Because it's got to call it, sees it fails, and then call it again. And then 80% of the time from that point forward, it's okay, fine, 10 seconds. But 20% of the time, it's going to go onto a third iteration. It might take 15 seconds. And so what we ended up doing was, what if we just race 5 futures? Like, just call it 5 times all simultaneously and hope that even just one of the 5 succeeds. And if all 5 fail, which is very unlikely, 0.2 to the power of 5. So in like 0.03% of the cases, sure, run it again. But now it almost always just takes 5 seconds, because the most likely scenario is that at least one of the 5 will succeed. And so, yeah, being able to compose things with these higher order like functions, these higher order functions for operating on many futures simultaneously is quite convenient. So yeah, things like select, things like join. Join's also a nice one. Join in terms of a thread means wait for this one thread to finish. Join for futures means wait for all these futures to finish. But start executing them all, like work on them all at this, concurrently, and then come back to me when all these futures here are finished, which is, again, quite useful, similar to a thread. And yes, workarounds for other people's bad code can be very fun for sure. All right. Any more questions? Half past. We've had some fun here today. I think the last half hour has been mostly like, messing around and answering some questions and stuff like that. Definitely is not always fun though. Yes, that's also very reasonably true. Cool. Any last questions anyone wants to get in? If you have an idea of something that you want to write, you want to see written in Wednesday's lecture to sort of like end things off, then again, let me know on the forum. My take is maybe something like a paste bin, using a web framework and async await and async rust and all that. My favorite web framework is Rocket currently. Rocket's a little sussy because it's gone sort of like on hiatus for certain periods of time, and it looks like it might even sort of currently be on hiatus again. Where like it's sort of run by one person, and when they get busy, with their personal life, the development for the web framework kind of stalls out a little bit, which is potentially a little disappointing for for like an open source project if you want to use it, widely in production. But I really like it because it's a really nice sort of gives a high level feeling to a web framework, and also takes advantage of a lot of really cool Rust features. So I was thinking we make something like a paste bin website using Rocket and Async Rust. But if you have any other ideas, or potentially any better ideas, then you can please feel very free to suggest them on the course forum, and I'll have a look out for that. But that's sort of my default idea of what we'll end up doing on Wednesday to end things off. Cool. All right. Not really seeing any other questions. Make an IRC server. I was also thinking of making an IRC client. Could be interesting. Maybe that can also be a separate thing. We could also do like separate live streams or separate recorded videos or something like that. But an IRC client could also be fun. All right. Let's leave it at that. Thanks everyone for coming. Hopefully we had some fun with this, even though it's, again, completely outside course material and not assessed or anything like that, but just because we have some extra time and some time for activities and fun. Yeah, thanks for coming, and I hope to see some of you on Wednesday again when we get to write some more Async Rust. All right, catch you all later. See you later. Bye bye.